In this video, we will look at the various geometrical relationships between two lines. Between two lines, there are several ways they can intersect with each other. The two lines can intersect at one point, for example, something like this. They intersect at this point over here. The two lines can also intersect at infinite number of points, or essentially, they are the same line. Or, the two lines can have no intersection point. However, unlike in 2D geometry, two non-intersecting lines does not just mean that the two lines are parallel. In 3D space, two lines can be non-parallel and yet they intersect. They are called skew lines. You can imagine it to be something like this, where I have a line lying over here and another line that comes out of the page like this. And we can clearly see that these two lines are not parallel and they do not intersect. So these are the possible cases of intersection between two lines in the 3D space. To evaluate the intersection between two lines, we can make use of the GC's simultaneous equation solver after equating the equations of the two lines together and forming three linear equations. For example, for lines r equals to 1, 2, 3 plus lambda multiplied by 4, 5, 6, and r equals to 3, 2, 1 plus mu multiplied by 6, 5, 4, I can equate them together and compare the three components to get these three equations. Notice that these three equations are linear equations and they contain two unknowns, lambda and mu. Thus, we can rewrite them in this form and key this system of linear equations into the GC to solve. However, unlike the chapter of system of linear equations, we might not get unique answers and we will need to know how to interpret the results shown by the GC. The first type of result we can get from the GC is the familiar one, where we get a unique value for each of the variables, like this. This means that the intersection of the two lines has one unique solution and thus intersect at one point only. Next, we may get a screen like this, where x1 is written in terms of x2 and x2 is equal to x2. This type of output means that there are infinite solutions, since lambda is equal to negative mu and mu can take all real values. And thus, these two lines are essentially the same line. Finally, we can also get a screen that says no solutions. This simply means that the two lines have no intersections at all. And once we determine that the two lines have no intersection points, we have to determine if they are parallel or skew lines, simply by comparing their direction vectors. If their direction vectors are multiples of one another, then the two lines are parallel. If the two direction vectors are not multiples of one another, then the two lines are skew lines. In example 1a, we are asked to determine if L1 and L2 intersect. So what we can do is to equate the two equations together. 1, 2, 3 plus lambda 1 minus 1, 2 equals to 2, 2, 11 plus mu minus 1, 2, and 4. So from here, we can compare the three components to write down the three equations. 1 plus lambda equals to 2 minus mu, 2 minus lambda equals to 2 plus 2 mu, and finally 3 plus 2 lambda equals to 11 plus 4 mu. And we can rewrite this system of three equations in a form that we can key into the GC, which will look like this. Lambda plus mu equals to 1, negative lambda minus 2 mu equals to 0, and 2 lambda minus 4 mu equals to 8. And we can key these three into your GC, which will give us the following solution screen. And this tells us that there is a unique solution and therefore L1 and L2 intersect at one point. And if we were to proceed to find out the coordinates of this point, we can substitute either lambda equals to 2 or mu equals to minus 1 into either equation. So we can say that r equals to 1, 2, 3 plus lambda, which is 2, 1, negative 1, 2, and this gives us 3, 0, 7. So 3, 0, 7 is the intersection point. In this example, we can also equate the equations of L1 and L3 together. 1, 2, 3 plus lambda 1 minus 1, 2 equals to 3, 0, 7 plus mu minus 1, 1 minus 2. And let's compare the three components and write down the three equations. You'll get 1 plus lambda equals to 3 minus mu, 2 minus lambda equals to mu, and 3 plus 2 lambda equals to 7 minus 2 mu. And we can rearrange this equation to become lambda plus mu equals to 2 minus lambda minus mu equals to minus 2, and 2 lambda plus 2 mu equals to 4. And again, we can key these three equations into our GC, which will give us this solution screen over here. And this tells us that there are infinite number of solutions. L1 and L3 intersect at infinite points, and therefore this tells us that L1 and L3 are the same line. Same thing for this example, we can equate the equations of the two lines together. 1, 2, 3 plus lambda 1 minus 1, 2 equals to 3, 0, 8 plus mu minus 1, 1 minus 2. And therefore, we compare the components to get 1 plus lambda equals to 3 minus mu, 2 minus lambda equals to mu, and 3 plus 2 lambda equals to 8 minus 2 mu. And we can rearrange these three equations to get lambda plus mu equals to 2, minus lambda minus mu equals to minus 2, and 2 lambda plus 2 mu equals to 5. Now we can key these three equations into the GC, which gives us the following solution screen. And therefore, we know that L1 and L4 don't intersect. Now, for two lines that don't intersect, there are two possibilities. Either they are parallel or they are skew lines. So now we have to compare the two direction vectors, and we see that since 1 minus 1, 2 is equals to negative of minus 1, 1 minus 2, L1 and L4 are parallel lines. Yeah, example 1D is the exact same thing again. So we have 1, 2, 3 plus lambda 1 minus 1, 2 equals to 2, 2, 8 plus mu minus 1, 2, and 4. So we can quickly do a quick comparison of the three components. 1 plus lambda equals to 2 minus mu, 2 minus lambda equals to 2 plus 2 mu, 3 plus 2 lambda equals to 8 plus 4 mu. And we can now rearrange them. Lambda plus mu equals to 1, minus lambda minus 2 mu equals to 0, and 2 lambda minus 4 mu equals to 5. And we can key these three equations into our GC now, which gives us this following solution screen. And therefore, we know that L1 and L5 don't intersect. Now, if they don't intersect, we have to check whether they are parallel lines or skew lines. And we can say that since 1 minus 1, 2 is not equals to k times of minus 1, 2, and 4, that means they are not multiples of one another. L1 and L5 are not parallel, thus they are skew lines. Between two lines, we can also determine the angle in between them. This is the same as finding the angle between the two direction vectors of the lines. Thus, we can make use of the dot product formula to determine the angle. However, one thing to note is that for angles between lines, questions usually will ask for acute angles, and thus it is convenient for us to place a pair of modulus outside the dot product in order to make this term positive and thus obtain an acute angle. In example 2, we are now asked to find out the acute angle between the lines L1 and L2, and so we can make use of the dot product formula straight away. Theta equals to cos inverse a big pair of modulus to make sure we get a positive term, 1 minus 1 2 dot product with minus 1 2 and 4 divided by the modulus of each one of them, 1 minus 1 2 and modulus of minus 1 2 and 4. This can be simplified into cos inverse 5 over square root 6 square root 21, and therefore just by pressing our calculator we should be able to get 63.54 degrees, or we should round it off to 1 dp, 63.5 degrees.